Okay. So I think we're going to start. Today is it's a special day because it's Thursday, so maybe most of the institutes are not aware that today is actually we have a talk, which is a pity because it's not that we have Professor Li Xiaofeng here very often, and I'm sure he's going to give a really nice presentation. So let me just say a few words about Li Xiaofeng. He has a PhD in physical oceanography from actually North Carolina State University. So he's actually been working over 30 years in the States, and now he's back in China for what, 4 years? So he did his PhD in North Carolina, but then he went and worked for NOAA, and we actually share some collaborators and colleagues in NOAA. Besides this, I would say, of course, you can check his CV, which is very extensive. But our, let's say, connection is through a program called Dragon, actually. Dragon is a sort of a program shared by the European Space Agency and MOST, which is the Ministry of Ocean Science and Technology. And it's a very nice program of exchange of satellite data between both, let's say, agencies, which actually now I think is in his 6th framework already. So we had a very nice project related to SAR, synthetic aperture radar, so high resolution images over the ocean, and he's probably going to explain quite a bit of these today. So I'm going to just let him do the talk and not me. Yeah? So thank you, please go ahead.
Thank you very much, Marcos, for inviting me to be here, give a seminar. Today I will present a general topic on artificial intelligence oceanography. So this is a work our team has been working on since 2019. Again, I'm Xiaofeng Li from Institute of Oceanology in Qingdao. So this is the content of my talk. The first part, I'm going to just very brief touch on what is AI, what is big ocean data. Then I will divide the deep learning in oceanography into 4 tasks. They are classification, image classification, data fusion, algorithm development, and lastly, ocean forecast. This morning I had an opportunity to listen to Marcos's group's presentation. Their work are more or less related to one or many of these subjects. So lastly, I'll just give a brief discussion and a summary. So let's start with AI and big ocean data. So this is a diagram I copied from the ECMWF. So on the right-hand panel shows the data that we received from the operational satellites. On the left-hand side, for example, the red orbits is the polar orbiting, the blue one is the geostationary orbits. So collectively, we have over 200 satellites on orbit with the goal for Earth observation. So we have a lot of data, which is represented by the 100% blue bar on the left. And then the data got selected and then imported into the ECMWF simulation system. And you can see the data that actually play a positive role is very less, percentage-wise is very less. So the question comes is, how do we use the data more efficiently? Here comes the big data and the AI. They go hand by hand, okay? First, we are in the big data era because we have so many satellites, so many model results. And if you don't have any tools to mine information from the data, then the big data just become a big garbage can, okay? Everything goes in, nothing comes out. And then the AI is actually the driver that is based on big data. You need big data to develop the AI technology, and then you can use this technology to go back to the, let me grab the point. Okay, to go back to this big data and then dig the information out. Because our human brain, we do not handle data very well. We can only handle information. So the AI and big data, they go hand in hand, okay? And with the advancement of this AI and big data, our world changes. The IT world changes. So traditionally, we have a traditional IT represents information technology, represented by the Intel, Microsoft, etc., those big companies. And then gradually it goes to the internet technology. And today it's intelligence technology. And you can see those big leading companies change as time goes by. And then the AI has been broadly intervened or entered our life through machine translation, face recognition, speech recognition, and the weather. Most recently, the weather forecast. Where Google has GraphNet and China has a Pangu, big model forecast. Okay, so those are the application of AI. And then let's dive into the deep learning oceanography. So this is the diagram we put together in 2018 in IGAR's symposium. At the time, we just started doing this AI because we have very little information on what AI was. Because as oceanographer, we enter in this field very late. Okay, as the rest of the computer world they took off a long time ago. So this is a diagram we put together. In the middle is the green part, are the libraries that's already developed by the Microsoft, Facebook, etc. Then I put an ocean deep learning layer in between, and those small things are the tasks we divided. Algorithm development, image segmentation, data fusion, and forecast. And those purple things are the modules that are already developed by the AI community, so we can adopt it and use it. So at the time, this whole diagram tells us it's very easy to apply AI technology in solving ocean problems. Okay, so and then you from this, for example, from this classification work, we can use the existing, UNet, and to solve these type of remote sensing problems. For example, the internal waves, the DEMs, the oil spill, etc. So at the time, we want to see this is not too difficult. Okay, and this is a roadmap for all groups' work down the road since 2019. Okay, remember this is 5 years ago. And then this diagram is we published in 2020. The x-axis shows the timeline, and those are the number of sensors that take the Earth's measurement. For example, the sea surface temperature or sea surface salinity. 20 years ago, we only have like 1 or 2 sensors. Right now, we have a lot of sensors that take measurements in high spatial resolution and high spectral resolution. So we have a lot of data. And then this represents AI development over the years, with significant event highlighted in here. For example, in 2012, Google has an ImageNet competition, organized by Xiaofeng Li, that is worldwide competition in image classification. So this event, the result of this event shows that for image segmentation classification work, human cannot beat machine, period, okay? And then you have the AlphaGo defeat the world champion. You see, a lot of event happens so until 2020 at the time, so these two diagrams meet. So it's exploded. We put some Taiji in here, say big data, deep learning, and then generate those applications that we highlighted in this review paper in 2020. Okay. So first, let's look at the classification. Remember, we divided the work into 4. So I will briefly touch on each of them. So this is 2019, remember. Okay, so we see, okay, we have 2 types of framework that are already developed by AI community. For example, this is UNet. It's very successful, used by the hospital to look at the medical images to see where the trauma is. And this is a targeted detection algorithm. So what we can do is we just borrow it and see what we can directly apply to real-time tasks. So this is a Hurricane Harvey that hit the city of Houston, and it cost over 23 billion US dollar damage. That's huge, okay? So This is the Hurricane Harvey damage. So what we do is we collect the satellite images. In this particular case, it's static aperture radar images before and after the event. And then you remember we have already 2 existing framework. We twisted a little bit with these red ones because we know what SAR actually is, instrument is. So we can calculate these physical parameters from the SAR imagery as an input to this framework, okay? And then you can find the flooding area, inundation area. Before, sometimes there was no water, then the hurricane came and then it's flooded, and you can all do this, okay? It's very straightforward. So this is 2019, and we wrote this paper in JJR, and it was published without any revision. But today, obviously, it doesn't work that way anymore, okay? But AI, the network, once you developed it, it can be used elsewhere. For example, if you teach a network what a dog is, what cat is, so he remembers it. Next time you see a cat and dog, it doesn't matter whether the dog is in Spain or in the States. The network recognizes it. So we developed this for the Houston, and then we apply the same network to the Hurricane Lichima inundation in the coastal city of China. And it gives you very good result as well. So it's very encouraging. We don't need to do a lot of work. We can then apply this to Madagascar for the coastal flooding before and after the hurricane event. So that becomes very simple, right? So to do that, one thing I did not mention is you have to create a lot of labels, so-called ground truth. So once you have the ground truth, then you can build your network. But to do the ground truth work is very hard. You have to manually, using some softwares, for example, Label Me, to manually get these labels out, and then you train the network. So the training process is very long, but once you finish the training, the application is very fast. This whole image processing just takes a split of a second, you can finish. But the training takes longer time and requires GPU computers, okay? And then the second example The second example is to look at those internal waves on the satellite imagery, whether it's on the ASAR or it's on the MODIS Terra Aqua. They all show different magnifications on the ocean surface because they create these convergence, divergence fields on the ocean surface. So it has this information on the image. So the task is to extract those internal wave crest, and then you can do further analysis. Okay, and then we again use this so-called UNet network. All the red part are the ones that we modified to fit the data type that we use. So for, if you look at the bottom three, you have a SAR, you have a MODIS, and then you have a geostationary satellites. So you tell the network, those lines are the wave crests, and we collected 15,000 images. Sorry, not 15,000. We collected about 1,000 images. We hand drawing those wave crests. We fit in this framework, and let the framework learn. Okay, and then fit its super coefficients. We got all of them, and then this network is built. Once it's built, we can just apply it to all the images on the fly. This is from the Google Earth engine. You can get 22 years of MODIS images all in the South China Sea. You can just fit in this framework, and it will derive all the internal wave crest for you. So it doesn't matter where it is. This is real time. You can do it on the Google Earth engine. You load, you bring in the data into the Google Earth engine, and then you apply the program. So this can be done anywhere in the world. Yeah, but right now we did not put it on the Google Earth engine because somebody ran it. I have to pay for it. So this is But nevertheless, you can do it yourself. Okay, once you have that, we can also extract the tidal flats. This is some agriculture area outside mainland China. We have a lot of sandbar regions in the area. So when the tide comes in, the coastline changes. So this is very important, and the tide is flood in and out with large magnitude, so it's very hard to do. So we collect a whole bunch of satellite images, again use the similar framework, with the red is the ones that we twisted because in this particular case, the coastline information is very tiny compared to the whole image. So we have to do some tuning to make the algorithm work. So and you can see those once you finish this tuning, and you can see this with the tide comes in, goes out, you see that the land change, the coastline change. And the yellow ones are the ones correctly did, and the red ones are the ones we missed. So you can see that the number is quite well. It's over 90% accuracy. Okay, so once you know the coastline and you have a good tidal model, so you can collect a lot of images, you know the coastlines, you know the tidal elevation, then you can fairly simply derive the DEM. Okay, this is you do it without going out to the sea. Okay, as long as you have a good tidal model, that's good. Okay, so the error is 30 centimeters on average. So this is to do this type of survey. This has never been done in the history. Okay. Okay, so this is another example showing the ice detection in the Arctic Ocean. So the Arctic Ocean, we have a group of people looking at how to separate the first year ice with open water. So this is the SAR images on the background, and this part is the one that we built. Okay. Similarly, we use SAR, and then again we use this UNet framework, and you can see the network gets a little bit complicated, and once you train what is the water, what is the first year ice, again you have to do it manually. But to do a ground truth label is kind of difficult for the sea ice. We have to bring in the NIC, National Ice Center in the States, their analysis field, and sometimes bring in the University of Bremen products, and then work by manually to get these labels out, and then we feed into this modified framework, double attention framework, to get it a little bit more complex, to get more information from the SAR imageries, and then you can do the ice and water separation. Okay, and this shows you the time steps, the time steps of this analysis result. And you can use it, again, once you build the framework, you can apply to the SAR imageries and get the ice and water separation over an entire season. This is separated by a few days, 3-4 days. You can do like 2 months analysis. Okay. Okay, so, and then this is a latest work that we try to make this framework even more better, because one reviewer keep on asking us to put the ice lead in it, which is very, very difficult because those are the very thin lines in the ice. So, we spent a year actually to work on it, and the algorithm still looks similar to previously, but we have to build in the 2 branches way. So we call it double branches to look at the signals from the backscatter, VVHV, the polarization, and also we look at the grid level GLCM, the image pattern matrix that you compute from the SAR imagery. So you not only look at the strong physical retrievals physical retrievals from the HV and HV. This is backscatter. This is the physical quantity. And this is the image texture information. So you put them together, and then you can get the first year and multiple year ice separation, and also get all these leads, these very tiny, long leads from the image. Okay, so this is very, very hard work because you have to build a lot of labels. But once you do it, you can get this. So we applied it in the Beaufort Sea, because Beaufort Sea, you have a Beaufort high pressure. It drives the rotation of the currents and also the sea ice motion. So you can build a very high resolution. Actually, we build a very high resolution Beaufort Sea ice product, first year ice, multiple year ice, etc. product at a very high resolution. This has been compared to the NIC, National Ice Center in the US, and the University of Bremen product is all very well compared and validated. But this is very, very high resolution. As you know, SAR has very good resolution. So up to now, I'm talking about the image segmentation, classification, right? Internal waves, coastlines, sea ice. I have many, many examples, but those are the ones get to know that some of the AI applications, we can just get it, make some modification, and then to solve real-time, real-world problems. So the second part is to look at what's the target detection. Okay, so this is a research vessel. It's 100 meters long, and it got this fancy, ROVs going dive to the deep side of the ocean. So our task, I don't know nothing about marine biology, but they ask us, can you identify some species down below, and if there are new species, this marine biologist wants to know if there. So these things goes to the sea mountains. Sea mountains are defined by mountains over 1,000 meters above the ground, but underneath the water. Okay, so there are over 30,000. Well, I changed it to English, but it changed it back. There are over 30,000 sea mountains in the world ocean. Among them, less than 1% has ever been sampled. So, they have very diverse biological activities down there. So our job is to see, where they are, identify who they are, and if they are they new species? So we have to do an AI model. So these are the areas our research vessel went. In Mariana Trench, this is the deepest part in the world. And those are the things we collected. They have called classes and species. Okay, there are 19 classes and 518 species, but some of them they look the same, and some of them have acquired the signal under different light conditions, because sometimes you put a light on them, they change the color, so that makes the work a little bit difficult. So those are the remember the UNet I mentioned is pixel level detection. I mentioned another framework. It's called SSD or YOLO. Just pick up what's in the image. Okay, so those are the things we don't need to do. We can just get it from the AI community. So once we get all these examples, shut down. It didn't like it. Yeah. No, I think the system is off. Oh, okay, great. Okay, now, thank you. It's good, thank you. So which framework do we use? This is the framework we use. It's called YOLO. This is an area in Pennsylvania. This during the pandemic. I drove there because I cannot do anything. I just drove there to watch the goose, Canadian goose, flew from southern U.S. to Canada. Then I went there. I asked the park ranger. I said, "How many goose is there?" They said, it's 190,000. I said, "How do you know?" He said, "I worked there for so many years. I know." Okay, that's his answer. Then I thought about it. There's a newest, at the time, okay, this is 2021, I think, a newest called YOLO framework developed by a US scientist, which is very, very famous. YOLO demonstrated you only look once. So I told the ranger, you only look once, you know. So, but anyway, we get this idea, we adopted the YOLO network. Again, those red part are the ones that we add in to deal with the image ambient lights. For example, like I said, you have a camera look at the animal at different angles, they look differently, the background color differently, and they change color. So we have we use this existing YOLO network, added those modules to do the species detection first. We need to find them first. After we find them, we can tell the successful rate, okay? But once you find them, it doesn't mean anything, right? Because everybody can find it. So we need to group them. We have to calculate, for each image, we have to calculate the image characteristics, which is represented by those line. I'm not sure if you can see it, the line and the shape of this characteristic features. Okay, once you calculate these features, each image has its own feature. Okay, then we can put them together to look at this feature similarity. If and if we arbitrarily set this number, we do a cut here, and if this is beyond this curve, we said it's possibly it's a new species. Okay, so after these three networks, we bundle them together, we have a successful rate of over 50%. Okay, it's not very high, but at least gives you a good starting point. So this is, again, using an existing YOLO, you only look once, a framework with modification, and then you can solve these real problems at sea. Okay? So I mainly talk about two parts, image pixel to pixel extraction, tells you the wave crest, the coastline, and then the second part is to identify objects in the image or in the video. Okay. So the second part I'll talk about data fusion. This is the work we look at the ocean eddies. The ocean eddies can be detected by altimeter, sea surface temperature, and chlorophyll A images. So they represent the dynamic, the thermodynamic, and the biological response caused by the eddies. So if you study physical oceanography 101, you know if you have an anticyclonic eddy, you have a positive SSH anomaly, and then you have an SST positive anomaly, and vice versa. So basically, it's on the left-hand side of this side. Okay, you have anticyclonic eddy, you have a positive SST, positive SSH, and vice versa. But in real world, we also have what we call abnormal abnormal eddies. In this case, you have a negative SST anomaly, positive SST height anomaly. So then we want to see how many of these abnormal ones are in the real ocean. So what we do is we get the SSH data in, SST anomaly data in. Then we use, this is a typical convolutional neural network. You extract the features from both images, you combine them, and then you put it into the UNet, and then get the result out. And then look at this. We have so many normal and abnormal eddies in this world. And just to put a number, there are 1/3 eddy in the global ocean are abnormal. So, once we got this result, we are very surprised. And we look at where they are, these abnormal eddies, where they are. It turns out they all stay in the strong current area, for example, western boundary currents, ACC, etc. So then you can look at the evolution over time. This is another one. We look at the abnormal eddy and normal eddy, their vertical structure, So they correspond to these four diagrams. So we can do this analysis. This is in the Indian Ocean. We have, in the Indian Ocean, this is, I forgot the name of this Gulf of Oman, I think. You can get these eddies, and then you can overload those eddies on the Caulfield image. And then the Caulfield image, you do some, time composite to get rid of the cloud, and then you overload these Caulfield maps on those different types of eddies. And in the meantime, you can put in the BCG algo to look at the vertical structure, and you can draw a lot of conclusions from this analysis. So this, again, there's no physics, okay, no equations, nothing. So far, no equations today. I only talk about data science. Okay, so from this data point of view, we can know what type of eddies in the ocean, and whether how can these eddies affect Caulfield A field differently, okay? And this is another one that once you have the dynamic SSH, thermal SST, and Caulfield A, which is biological, and also you have the BCG algo profile. So the next case is just how to build a 3D eddy structure using the deep learning network. Okay, so this is the test data set in the Crucial region. Crucial, another western boundary current in the North Pacific, and you have a Crucial extension, and then you have this OC, which is another current coming from the north. So the eddies in these areas are quite different. So if you get enough eddy signal, BCG algo data, you can look at the satellite measurements with the SST, SSH, etc. And also we can compute using some basic equations to look at the EKE, velocity, etc. Simple calculation, right, from the altimeter data. You calculate it, you put them in the full connected layers. This is another CNN with some attention mechanism. Then you merge them together. These two neural networks are very different. You put them together, and then you can draw like a 3D eddy model. From there, you can look at the 3D structure for different regions. This is Crucial extension. This is OC current. So you look at the anticyclonic eddy, cyclonic eddy. They behave differently, and how is their vertical structure. So this can all be done, okay? Okay, so this is the fusion. Okay, this one is another interesting example to show you how to fuse the data between the laboratory and the real world. Okay, this is Andaman Sea in the Indian Ocean, and we have one buoy there. It's called the White Dragon buoy. It's very expensive to maintain this buoy because it takes months for research vessel to go there. You just go there once per year, And this is the satellite image, and this is the buoy. Give us a very nice observation of these huge internal waves in the Andaman Sea. Okay, very significant event. But this is what we have in real world. Okay, but if we want to do some forecast or do some vertical profile retrieval from the satellite measurements, just impossible. So from 2D to 3D, it's just impossible, okay? So what do? We set up this laboratory, okay, with the camera resembling the satellite, and we have a side camera. We have two cameras. Side camera just resume this buoy measurements. So we have the vertical profile like this, and the surface magnification of the internal wave like this. So what we do is we forget about this one first. Look at the lab data. Again, there's no physics. We just purely data processing. We establish a model between the surface and 3D elevation. Okay, so it's just like you teach a kid how to identify a cat or dog. You don't show them the real dog or cat. You show them on the book, and you show them long enough. if you build a network like this, I won't go to details, then it knows what the internal wave surface and the vertical relation is, because this is what AI can do. And then what you can do, you build this model, but you cannot apply it directly to the real world because they are different things. They have different stratification, they have different skill. So then here comes this transfer learning method. It's basically you have a deep learning model, you train with the lab data, which is very cheap, and then you frozen the coefficients in most of these layers. Okay, say, okay, don't touch this anymore because it already learned. So I use the real-world measurements to only fine-tune the top 2 layers, just scratch the surface. So this is called transfer learning. It's widely used in the AI world. And this is a very famous guy who was the lead for Google Brain and also a professor in Stanford. So we adopted this, and we just did this transfer learning model. And you can see the error just goes down. Those are over 100-meter amplitude waves. The error goes down to less than 10%. That's very significant. And then, if you look at this, we can predict from the satellite surface measurements, we can predict, or not predict, we can estimate the amplitude of these internal waves. Okay. And if you apply the theoretical formula, in this case the KTV equation, it's very well known. It only gives you 10-meter amplitude, but in reality it's 40 meter. So this gives you very, very accurate result if you design your framework nicely. And this is just a scatter plot to show how we once we implement the procedures I described earlier and the result. So once you have it, you can then have the full two-dimensional satellite observation in the Andaman Sea. You can just apply it and then derive all the internal wave amplitude in the Andaman Sea, and then you can apply it to Sulu Sea. If the Sulu Sea or other seas are the ocean environment are very, very different from Andaman Sea, for example. The error is big. Again, you can apply transfer learning again. Okay, so this is a very interesting work that you can build on top of it and then just get the internal wave retrieval. So I give you a few examples to show how to combine different sources of data to give you this algorithm development work, data fusion work. Okay. So the third part is algorithm development. Okay. So this is the example, the scatter plot actually I saw into this morning's presentation. You have SAR measurements of hurricane wind speed, and at some point, you get saturated. The signal gets saturated. So no matter how big the wind increases, the ocean surface physical return is limited. Okay, so it's truncated. So there's no way you can estimate the higher wind. So in our old work, there are a couple of ways to do it. The first way is to look at the VH, gives you, for example, the Sentinel Redaset 2 with very high noise floor can give you this quasi-linear relationship. Another one I want is to look at the waves, to look at the waves generated by the hurricanes. If you get the waves, significant wave height and wavelength correctly, we can use the so-called triplet relationship to derive hurricane winds. And then today we have a third way to do it, which is neural network. The way I look at it is because the SAR measures not only physical return, it measures a whole bunch of things. For example, it gives you the GLCM, grid level coherent metrics, which represent the texture. They give you the different scattering metrics, and it also tells you where the hurricane eye is, where the rain band is, etc. Okay, so all this information if you put in the physical domain, you cannot develop an algorithm because they are not even the same thing. Some of them are not even physical quantity. So what we do is we put everything together. You measure everything, we give you everything to this neural network. And this is the result. Those are the left-hand side, the top left-hand side is the hurricane retrieval network. And those are the ones we developed, we published years ago with Paul Huang from NRL, Naval Research Lab in the States. And you can see it's increased the accuracy dramatically. Okay, it's even better. It's even better than the CMOD, for example. The CMOD only works for wind at a low to moderate wind speed, so it gives you very, very good result. It reduced the RMSE by 30%. Okay, so you can use it for hurricane wind retrieval from the SAR. Okay, so this gives you a very nice example just to show what neural network can do versus physics-based algorithms. I have to hurry up. This one is the last one is the ocean forecast. Ocean forecast is the most difficult one, just like a meteorological forecast. People are interested in knowing because we all want to forecast what's going to happen tomorrow, right? So we summarize the deep ocean in ocean phenomena forecast in three categories: point to point, field to point, and field to field. I'm going to just give a few examples and each. So the first points, 2 points, just means we have a whole bunch of one-dimensional measurements, and we want to use this measurement to predict what's happening in the future. So I use the internal wave as an example. So those are the internal wave. I don't remember this place, probably in the Sulu Sea. It doesn't matter. So we can get this wave crest from the satellite image, and then we know those waves are pushed by the semi-diurnal tide. So if you have a multiple observation, you know the tidal separation, tidal period between the two, so you know how fast they go. So this is one measurement. So then we collectively, in the 13 hotspots, internal wave globally, we use this number of images. We can come up with this number of samples. And then we have these samples, right? What we want to see is next time you give me a green curve, I want to know where the red curve will go, okay? So this is what happens. Again, I saw this, this diagram earlier in your group's talk to how to make things in different group. So first we clustering. So there are 13 hotspots, world oceans, and different types of internal waves. So first we automatically group them into different groups, okay, using this XG boost results. Once you have that, then next time you see an internal wave and its ocean surrounding, it knows which group it belongs. And we only train the same groups, internal wave, we treat them in the same group. We train them separately, okay? You cannot use one algorithm was trained and then apply elsewhere because the ocean environment, the surroundings are different. So once we do that, we can build this point-to-point, very simple, full connection model, very simple, and then it gives you the forecasted result, okay? And once you have it, you know anywhere in the world is, you give an initial location, it knows after one tidal circle or two tidal circles. Again, after you derive this framework, it can apply to different places worldwide. Okay, those are the examples. Those data, the images, the network has never seen because we never trained them using the information in these areas. So once you have it, again, you get the internal wave out, and then look at their structures, look at the ocean environment, and then put them into a different group, and then apply the neural network specifically trained for that group to do the forecast. So this is the result, and you can see it's less than 10%, okay? Again, once you have one tidal cycle, you can put into multiple tidal cycles to tell them where do they go, okay? Into the So the second, that's the point-to-point. It's very simple. Just use a fully connected neural network. It's, nothing fancy. It's getting more and more complicated. So the second part is what I call the field-to-point. So this example showing we want to forecast, for example, the typhoon intensity, hurricane intensity in 6 hours or 12 hours. Okay, so what we do is we collect all these images, 500,000 images, just to train the network, and look at those auxiliary information. We design, a neural network, CNN-based, to extract the information. This is what the network looks like, and once you do this, all this information extraction, you can actually calculate it. I haven't talked about the forecast result yet. You look at the network, okay? The network contains a lot of, each layer contains a lot of coefficients. So this is something called heat map. The heat map is to look at the maximum gradient within the network. So that tells you what model is doing, which places the model did this heavy lifting, okay? So once we have this, backwards. Once we have this so-called heat map, we can go back, but take this heat map and go back to the input and multiply everything by this heat map. It's like enlarge the areas the model is focused on. So once you have it, number one is explainable. We know what we're talking about, and then it gives you a very good estimation. Okay, the results of typhoon intensity forecast. Okay, after 20 hours. So I think, this is just published this month. This is very interesting. And the second I want to talk about is to look at the field to point. Another example, you cannot avoid it, is INSO, right? INSO is you look at the sea surface temperature patterns over last so many years, from the CMAP6 measurements, ocean heat content, SST. We developed this, it's getting very complicated. This model design is very complicated. It's like you design an electric circuit. You have to add a lot of things, to make it work. And then the result is, just believe it. Oh. So this is the result. So look at this group of diagrams. Those are the lower ones are the NASA NCAR models. So to do the INSO forecast, looking forward, they can only do 12 months, okay, forecast. And then in 2019, this green curve by the Korean scientist is published in Nature. They push this forecast length to 19 months. But their network is very, very simple. So after after this one, we put all the things together. We can push the forecast length to 23 months. Okay, so that's very important. So so this is from the field to point. The last one is the field to field, which means you give it a field and I want to forecast the field. So I'll give you an example. This is a tropical instability waves happening in the Pacific Ocean, right? So it's this type of crusty waves propagated from the eastern Pacific all the way to the west. Okay, these are the basic characteristics of these waves. It's very, very famous, and there's nothing no model can forecast this. So what we do is we build a CNN-based information, but in this design, we designed the model into 4 layers, all nested layers, very similar to when you run the numerical models. You have a different, nested layers, 27 kilometers, 9 kilometers, 3 kilometers, to do this nested grid. So this is the similar design because you change the field of view, the CNN will tell you different features contained in these satellite images. So after you do this, you can forecast the SST field down the road. It's a field-to-field forecast. And the top one is the satellite SST, the lower one is the forecasted. So you look, they're fairly similar. And once you have this, you can also do, calculate the major ENSO indices and compare that to the propagation phase speed of this, this TIW, tropical instability waves. So you can do all this analysis. So I won't go to details, but once you have the forecast, you can do it. And also you can look at the phase speed, whether it's high in the high latitude and low in the equatorial regions, stuff like that. And then you can look at this, okay? It looks, the top one is the forecast one, the lower one is the satellite observation. They look similar, but remember this is 2020, I think, the paper. So at the time it looks pretty good, but today, no, it's outdated because why? It looks, this one is very blurry. Because CNN is, you actually do this convolution calculation, you need this matrix. You do a matrix operation, by definition, you smooth the boundaries. So this one can solve the TIW, but in the AI field, it really has a lot of shortcomings. And how to solve it, I didn't put it there. We solved it, okay? We use a very complicated network. I know you're one of your group guys is doing that. I can show him how we did it afterwards, but it's too technical here. Okay, so I gave a brief introduction on these 4 parts with examples, and then I have a few minutes just to go to the discussion and the summary part. Remember, we started doing this in 2018, 2019. The first diagram we published in IEEE TGAS, sorry, not TGAS, IEEE IGAS. And then in 2020, we built this so-called, overview of what's going on in 2020. And then last year, we published this book with Springer, which contains all the work that we published at that point. I think it's around 60 papers, something like that. This paper is free. You can get it from the publisher website. It's free for distribution because I paid for it. And you can, the roadmap is like this. And I think the work that you guys have been doing, fall in one or many of these 4 subdisciplinaries. So I think, 5 years ago, we put our thoughts together, but we have actually leave a lot of blank, new things we don't know. So one of the things I think recently people are trying to do is data reconstruction. Should add it here, how to reconstruct the ocean big data. But at the time, we don't know, okay? And then people will ask, where do I start? This is a very simple question, right? I'm a domain scientist. Where do I start if I want to use neural network? So earlier this year, we wrote an article for IEEE magazine. Just tell you, to answer this question, where do I start? So this is the diagram from the paper, and I encourage all the beginners or entry-level AI people to read this paper. It won't give you the state of the art, but it will explain how you deal with things, do the forecast, do the super resolution, etc. How to do transfer learning, interpretability. So it tells you all that, okay? So what I think you should start from convolutional neural network, okay? This is where do I start. The second part is look at the back of the history. When I studied remote sensing 30 years ago, it was a lot of criticized. So you just look at one image, it's a cartoon, nothing in it. You cannot look into the depths, in the ocean depth. So this is a chart from the ECMWF. So 30 years ago, everybody criticized. 30 years later, if you look at this chart, all the major milestones that has been pushed are by remote sensing observations. So 30 years ago, people see remote sensing is useless. So right now, nobody sees that. So when I gave seminars on this AI, a lot of people say, this is a black box, so on and so forth. But 30 years from now, people will accept it just like we accept remote sensing in the past. And the second part is the so-called new paradigm. How do we react to this incoming AI technology flash? Okay, I put a paper here by an American scientist showing how this works. So, like us, we all domain scientists. We study hard. We go to colleges, PhD training, postdocs. Establish a career to solve problems. So this is so-called bottom-up approach. So we are domain scientists. It takes very, very long to be a domain scientist. But now we have a data scientist. The data scientists, they are not people who only provide data. They are data scientists. Like I showed you today, hopefully you guys convinced that data can help you solve the problems, because today I have never talked one equation at all. So if you look at right now, the big papers on these big journals, usually they are joint by those data scientists and the domain scientists. So data scientists, they don't care what data is, physical, biological, chemical. They solve the problem from the top to down approach. So this is a new paradigm of how we do ocean science. And then cares about black box, because people see, it's a black box, okay? I don't know what's going on inside. So this is the article by a professor from Carnegie Mellon University in Science showing how to define the black box. I won't read it, but just think about this. If you remember, a lot of things are developed in the medical field. If you go to a hospital, you do an exam, I mean, you want to get the best result, right? You want to get the best result. Do you care about the algorithms? Nobody cares, okay? So they give you the best result. Like the George Box, the father of statistics, he said, all models wrong, but some are useful, okay? So AI belongs to this type of category. So if you study physics, okay, your whole life is based on what you know. You derive the equations. So it's like a handle. You must hold it to move forward. But the AI is different. So hopefully, I put this. You have to, let some things you used to it, let it go. Just like Columbus said, you can never cross the ocean until you have the courage to lose sight of the shore. So this is the talk on my talk, and my information is listed below. And just send me an email, to discuss. And with Marcos, we will have a lot of collaborations down the road, hopefully, starting from the Dragon. All right? Thank you very much. This is a picture I took.
Thank you so much for this comprehensive presentation. Actually, there's a lot of information here, and you've actually touched many fields, which is really nice. So not just physical oceanography, which I guess the audience also appreciates. So we have some time for questions, I hope, if people are not too hungry. So anyone would like to pose any question? Marta?
Thank you. Very inspiring presentation about the eddies that you were detecting, abnormal eddies. I don't know if you know these Shelton last works saying that these eddies are actually dipole eddies. So maybe your algorithm is just like detecting one part and the other part of the dipole, or is just not the case?
Okay, yeah, that's a good question. Dipole eddies are different from these eddies we look at. Remember, we look at use the SST and altimeter data. So the eddies are fairly big. Dipole eddies are usually very small. So you can, if they are dipole eddies, we pick them out anyways. So it's not going to miss, all right? So I don't think majority of the abnormal eddies are just the dipole of the other part. Yeah.
Thank you.
Yeah, thanks a lot for the presentation. It has been quite insightful, I must say, and I think you have been quite thorough about a good amount of works which are quite interesting. I have also, it's more than a question, it's a comment, is that we tend to forget that most of machine learning really is based in statistics. They are statistical models, which we, of course, have a quite wide degree of complexity right now. But at the end, at the basis is just mainly that. And one of the things that I remember when I was studying multilinear analysis and multivariable analysis was that one of the things that is quite important is to start thinking first into the problem, to try to find the most simplistic model that you can use really to answer your key questions. No? And nowadays I feel that a lot of, in data scientists, there is the opposite. We just throw everything into it and then just hope for the best instead of trying to go deeper into this. And I want to know, in terms of this question, I'm really interested in the part of what it is developing physically informed models, so that you really stop first to think in the problem, then you try to get some understanding of it, and then you choose the right approach, which I found myself by my experience is far more optimal to get good results. But I want to know what's your experience in this regard, and what do you think about that?
Okay. Thank you very much for your question. It's actually very important. So the question actually two parts. The first part, why are you, if you can go simply, why you want to go complex, just to show you know. The second part is why the physics informed should be adopted in this neural network design. The first part, I agree with both parts. The first part is, if we can solve the things, with multivariable regression, we should do that, okay? Because there's no point you go through this hustle to build your database and just define a model that use a lot of GPU energy and just beat you by 1 point or 2 percent. There's no point to do it. Number two, I serve on the JGR machine learning and the computation editor. There are a lot of papers. They just, put the newest model in there without asking why we use this model. For example, there are a lot of transformer-based. Transformer is very high-level the ChatGPT is based. It gives you very good results. But some people just adapt it, and they apply it and give you a result, regardless of how complex it is, whether it makes sense to use it to start with. So we actually wrote an article just to address your question. You use this neural network, you have to know why you use it. For example, CNN. If I can use it to solve a realistic problem with look at the heat maps and the interpretable, I use that. I don't need to go to transformer-based. Okay, so you have to have some knowledge. From the journal editor perspective, you have to know what you're doing. Okay, either you have some ingenious design to improve your algorithm, neural network algorithm, or you use some sort of existing neural network to mine information from the ocean. Okay, this is number one. The second one is physics informed. Physics informed, we have actually done the work quite a bit on physics informed neural network. For example, how to solve partial differential equations using the physics informed. Actually, the original paper done by the professor from Brown University, he used the KDV equation. I described in governing the ocean internal waves. So, but it's very difficult. It's PIN, it's very difficult to do it. In this internal wave work, actually we used it. I didn't talk about it, but I used it. Used the KDV to provide like a first guess, like you said. And then the advantage of that is because once you have physics-guided approach, so your model converges fairly quickly. And the data you need reduces by quite a few order of magnitude. Just think, neural network is searching for solutions, globally, 300 degree, all space, in the whole world space. If you have a physics, this guy is governed by this physics law. It's like you shoot a light in the dark space, tell the neural network, okay, look for a solution in this direction. But right now, this is very, very hard research topic, and we are trying to do it. How hard? I tell you an example. We submitted a paper 1 year ago, and we couldn't find a reviewer until today. Nobody reviewed it.
No, yes, it's a good point, actually. In the European Union, they are trying to push a lot towards a physics-informed model because of improved explainability of the results.
Yeah.
But I think, at least from a perspective, there is a lot of things that we can do using, let's say, traditional physics before going directly towards integrating the information into machine learning or deep learning models, which probably can help a lot to optimize, as I said, the implementation and also to get better results, right? So instead of working just in the raw variables, just introducing some layers in which we can already inject information that we already know is gonna be working, instead of just collecting data and grinding the data through through complex processes.
Yeah, but if you know the physics that govern the phenomena you study, yes.
Okay, people are hungry. Any other question here?
I probably missed it, but I think at some point late in your talk you mentioned something about a flip in phase between ENSO and your prediction, 180 degrees.
Yeah.
If I got it right, there was, that 180. Can you say something about that? I'm interested in that flip, this out of phase.
Okay, that's the tropical instability wave. So during the ENSO years, this wave is very weak. During the non-ENSO years, those waves propagate very fast. So this is what I want to see. But this is from the research finding. But that's nothing to do with machine learning. But those are the, I'll show you. Yeah. So, I think the downstairs, the bottom ones are the TIW phase speed. The top ones is ENSO 3.0, NINO 3.4 index. So when you have a major event, those tropical instability waves, they are very weak. So this is what I try to see. Okay. So yeah, those are the things that you can, because there's no physics, so you can just find it, and then a lot of people carried on to these studies, and these JPO papers, GIO papers tell you what's the mechanism behind. Okay.
Maybe one last comment, because I know people in the audience in Zoom or whatever platform are interested in YouTube. And you actually mentioned that you see a sort of a dumping in the spatial scale. So it goes to, so the resolution is more like a larger scale than expected. And you said that you solved it. Maybe you solved it for the ocean, but we know that for the atmosphere this is not the case. So ECMWF now is struggling with machine learning models. They sort of give, let's say, a good solution, but they have a real dumping on the variance. And of course, atmospheric variance is an order of magnitude higher than in the ocean. Yeah. So this is something that is more acute for atmospheric problem solving than for ocean. So the problem is always in this loss function, of the machine learning process. But maybe you could say a few words on how to tackle this.
Sure, definitely. So there's a big difference in atmospheric machine learning and the ocean. Atmospheric machine learning, the state of the art is, there's a GraphCast, by Google, which ECMWF already put into their operational use. And also there's one called Pangu, developed by Chinese colleagues. It's already at the ECMWF. So those are models for what we call element forecast. For example, velocity, temperature, etc. But there are only 2 ocean large models. These are called large models. There are only 2 ocean large models. They try to predict the salinity, the temperature, etc. It's harder than what atmospheric people do. So the results are not very, very significant, but people are trying to do it. However, we do, our group, we do not think ocean element forecast model is really that useful, compared to atmospheric. You forecast the ocean temperature change, half a degree in 3 weeks. It doesn't really, nobody cares. So what I think is we ought to develop some large ocean model targeted on those phenomena, upwelling, internal waves, eddies, tropic instability waves. So those large, medium, and small phenomena are the ways to go for a large ocean model design. And right now, there are none in the world, so we're working on it. So as the infrared people, yeah. All right.
Okay, so thank you very much again for this beautiful speech. And anyway, now we have to close. Anyone who wants to go join for lunch, please come with us. Thank you.
All right, thank you so much.